So our last section here is going to be 4.9. 4.9 starts on page 78 in our book, okay, or in our handout, if you would, for that chapter 4. And we're going to be looking at the resultant of distributed loads, okay, distributed loads. So a distributed load, what is a distributed load? We're going to look at the top of page 79 in this handout. And a distributed load is going to be a load that is going to be one of two ways. It's going to either be evenly distributed or it's going to be triangularly distributed. So an evenly distributed load means that we're going to have the same amount of load evenly distributed over the entire length. So as we look here, you're going to notice that on the right-hand side, they call this variable, I don't really know why, maybe it's the weight of something, W, and its units are going to be in force over a unit of measure. So you're going to notice here we have either pounds per foot, newtons per meter, and then they're going to be evenly distributed over the entire length. So for instance, in this case, if I would take 1 foot and it's 10 pounds per foot, every foot that I would cut and I would weigh it would be the exact same amount. So it would be 10 feet, 10 feet, 10 feet, 10 feet. The total amount then is going to be however many units that I have of length multiplied by how much each one of those sections weighed. Okay, so if it was 10 pounds per foot and I had 10 feet, how many pounds total would I have? 10, right? Times 10 would be 100 pounds total. Okay, and I could then concentrate that 10 pounds at the geometric center, and that's what we see right here. The resultant of this evenly distributed load would be equal to its W, whatever its weight is per unit of length, multiplied by however long it is. Okay, so that's what we see here. Resultant is equal to W times L. And that W is going to be, for instance, its weight in units of force per units of length. Now, this is used a lot when, for instance, we have a beam. And the beam might be of considerable weight. So like an I-beam. I-beam is kind of big and chunky. And not only does it have to support loads that are on that beam, but it has to support its own weight as well. And so since the beam would be made of the same material over the entire cross section, we would simulate the weight of it evenly distributed over that entire length. And so we would say, you got to take the weight of the beam in account, and we would know what the weight of that beam would be per unit of length. And so then we could concentrate the total amount at the geometric center or halfway in from either side. Now, as we look at this, notice that this makes a rectangle, okay? And if we look at a rectangle, how do we find the area of a rectangle? We take the length times the height. Do you see how this is the length and the W is the height? The resultant is going to be equal to, if you would, the area underneath that curve or in the rectangle, okay? Now, when we have a triangular load, we start from nothing and then we ramp up to a value. Do you remember the area equation for a triangle? What is it? 1/2 the base times the height. So this would be your base, the length, right? The height would be here, and we would basically divide it by 2. If we would have the full rectangle, we would have just base times height, but because it's the triangle, it's going to be half of that. So our resultant here is going to be W times length divided by 2. Okay, or height times length divided by 2. And then we would concentrate it, not at the geometric center this time, because we have more on one side than the other. It would either be 1/3 from what I call the high side, or 2/3 from the low side. And that would be where we would concentrate for that distributed load. Okay. So this page is going to come in handy, page 79, to go back to when you're dealing with either a rectangular or an evenly distributed load or a triangularly distributed load, and how to, number one, get the concentrated load, or to, or to find its geometric center. Oh, hold on. I noticed that there's a question here. Lex, would we be able to reestablish which problems are practice problems? Oh, I will, Lex. We'll do that before I leave. And then, yeah, thank you, Josh. So I'll answer that after we're kind of done here. Okay, Lex? Right. And we'll go over the application problems and the practice problems. Thank you. That's a good reminder. So now, as we go back over to page 21, up here is just a review of those two things that we had looked at. And then now we're going to look at example 4.8 to really use these distributed loads and find the resultant. So example 4.8 on page 79. Zoom out here a little bit. We want to determine the resultant of the distributed load shown. So what we have here is we have the distributed load shown, and you'll notice that we can break this into two distinct distributed loads. If we take a line and we go straight across, we have one evenly distributed load, and then sitting on top of it is a triangular load. And that's what we see over here on the right. The bottom is going to be the rectangular, and the top is going to be the triangular. So having two distributed loads, what we're going to do is, instead of dealing with the distributed loads as separate forces, if you would, we're going to find their concentrated load at their geometric centers. And then we're going to have two parallel forces that we need to find the resultant for, which is going to be similar to earlier this evening. Okay. So really the only step here is to recognize the distributed load, find the resultant of that distributed load, put it at its center. And then when we have multiples, then finding the resultant of those multiples. Okay. All right. So as we look here on page 21, first things first, we're going to draw our free body diagram and add our convention. So let's see here. To draw our free body diagram, we are simply going to draw from A to B. Okay. The first one is going to be at the geometric center. This is going to be our resultant that's going to be for the evenly distributed load. Okay. We'll call this R1, like the book does. We're going to calculate R1 in just a little bit. And then our second is going to be for the triangular. Okay. And I'm going to make it just a little bit taller. This is going to be R2 is equal to. Now, we don't know their distances just yet. We'll talk about that in a little bit, but we do know the distances between A and B are 4.5 meters. Okay. We're going to put our convention in the upper right-hand corner. Okay. And now we're going to determine the magnitudes of R1 and R2. R1 is going to be equal to W times L. So going back to our problem, we need to determine what W and L are. Okay, I just see there's a couple people writing. I'll wait before I put this down. Okay. And now what we're going to do is our rectangular load is right here. So our W is going to be equal to the 5 kilonewtons per meter. Okay. Our length is going to be the 4.5 meters. So it's going to be 5 kilonewtons per meter times 4.5 meters. Meters cancel out. We're going to multiply these two together. Our R1 is going to be 22.5 kilonewtons. And that's your number right there. 22.5 kilonewtons. R2 is going to be WL over 2. Now, to determine its W, we got to go back to the illustration, because the 19 kilonewtons per meter is the total height here. So its W is actually this difference from here to here. So we're going to take 19 kilonewtons per meter minus the 5 on the bottom, because we need to be at the bottom of the triangle that's sitting on top. So that's going to be 14 kilonewtons per meter. So 14 kilonewtons per meter times the total length is still 4.5 meters divided by 2. Meters cancel out, we're left with kilogram or kilonewtons. R2 is going to be 31.5 kilonewtons. Now, any questions on the magnitude of the resultants? So we took those distributed loads and we made concentrated loads out of them. Now, distances, we need to locate them with respect to their distributed load scheme. So the R1 is the rectangular. That's the easy one. The rectangular is always going to be located at the geometric center, which is half in from either side. So since we are at 4.5 meters, that means that from A to R1, that's going to be 2.25 meters. Okay. R2 is the triangular load. Now, since we're going to be going from A, with our moment, we will be, we want to have the distance from the low side, which is going to be 2/3 the distance, 2/3 the overall length. So if we take 4.5 and we multiply it by 2/3, we should get 3. Is that right? 3 meters to A. So now we have our resultants located. We know exactly where they are. And now to determine the resultant of these two parallel forces, we're now going to use that process from the beginning of this evening. So I'm going to zoom out a little bit. And our next step is, since we have a parallel force system, we're now going to determine that resultant by summing the forces in the X direction. In what direction? Y direction. That was a typo. That should be the Y direction. So we're going to sum our forces in the Y direction to get our resultant. If our forces were in the X direction, we would do the X, but they're in the Y, so they should be done in the Y. So we've got a negative 22.5 kilonewtons, a negative 31.5 kilonewtons, and equal to R. So my number is going to be negative 54. Is that right? 1, 2, 3, 4, 5, yeah.
53.75. 53.75.
Really?
But it's a minus 31.5.
31.5. Yep, 31.5.
Right.
Okay. There we go. Now that's the resultant. So now we have to determine where are we going to locate that resultant, right? Now we go back to our R bar. So on the next page, we want to determine the moment that's generated by those individual forces. So we're going to do sum our moments around A equal to. We're going to put our finger on A, and we need to know what these are, how these are going to rotate. So 22.5 times perpendicular distance of 2.25, and it's going to rotate negative. And then our second one is going to be 31.5 kilonewtons times, I just know the magnitude, so I gotta go back over here, times its perpendicular distance of 3 meters, and it's going to rotate clockwise, which is going to be negative. So negative out front, 31.5 kilonewtons times 3 meters. So some of my moments around A, I'm going to have negative something. 145.125, okay, thank you. And that's gonna be kilonewtons times meters. Awesome. All right. Now I'm gonna determine the location of the resultant using sum the moments around A equal to my resultant times my R bar. Looks familiar, right? So I'm gonna take this number and put it here. I'm gonna go back and my resultant was a negative 54. And then my R bar will be the only unknown. So negative 145.125 kilonewton meters is equal to negative 54 kilonewtons times R bar. Yep, 2.69, 2.688, good. And then now we're gonna draw a quick diagram, right? So we're gonna go from A to B. We're gonna draw our resultant was equal to 54 kilonewtons. And my R bar is equal to 2.688 meters. There you go. Okay. Now, I think it's a great idea, like Lex had asked, like which problems are part of our practice problems and which aren't, because we did skip over 2 of them. And then we inserted 2 of our application problems. So let's take a peek at our handouts here. I gotta maybe get mine in a little bit of order here so that one. So I'm gonna pause the video for just a bit and then I just wanna get my stuff in order. Okay, so since we had kind of skipped 2 problems, 2 example problems, I wanna be sure that we know which ones we're handing in our practice problems. So based on our guided notes, page 1, okay? Page 2, and our first example here is 4.1, right? Page 3, okay? Example 2. And then example 3, which is, we're up to page 6. Example 4, page 7. We did our quick review on page 8. We did problem 4.5. Okay. Page 11, we filled this in for section 4.5. Page 12, we did example 4.4. That went over to page 13. On page 14, we skipped 4.9. So you can cross off that. We skipped 15. You wouldn't have to do any of this. Page 16 at the bottom, we resumed and we looked at, and we did example 4.5. Which then took us to page 17. We filled this all in. We didn't break into components just to save a little time. That's why I crossed that off. So you don't have to do that part. And then we finished that problem up at the bottom of page 18. On page 19, we skipped 4.15. Okay. Because then we inserted another application problem. So you don't need to hand in that application problem as part of the practice problems. You can just put that as part of your homework. Like we got 2 homework problems done for you guys tonight, okay? And then nothing on page 20, okay? And then page 21 was the distributed loading that we just looked at, finishing up with example 4.8. And then page 22 filled out. Okay, so the two examples that we skipped were 4.9, problems 4.9 and problems 4.15. So if we go to, if you're someone who wasn't doing the papers, that's okay. If we go to our practice problems, I'll remove those from our module. I can do that right here. So I'm going to take off 4.9 and 4.15. Okay, the rest of them then you would be responsible for that we did during our lectures from the last time and this time. Okay, thank you for asking that, Lex. I think that's good clarification. What is the due date for our homework? All right, yeah, because I wanted to see, I know I talked in the beginning about possibly changing it because, you know, depending on how far we got tonight. So lucky thing we got through everything. So what I'm going to do is let's go look at our calendar. And you'll notice that our module 4 homework application problems and practice problems are set to be due tomorrow. That's kind of our normal due date is Fridays. Okay. I don't know if you guys like it or not. I randomly pick a date, and that's why I have the flexibility of the grace period of 7 days after, so that if that day doesn't work out for you, you can always work on it over the weekend and get no penalty. I'm not going to move it because we got through everything tonight. Okay. And we worked on a couple of those problems. So, but what I will do, this is what I will do, is I'm going to increase the grace period from 7 days to how about Monday, the 26th. You can still ask me questions. And so you can actually hand it in until the 26th, the end of the day on the 26th for full credit. So you would actually get 7, 8, 9, 10 days instead of 7. Does that sound fair? Are you okay with that, Josh? So a little bit of extra time on the grace period. Yeah, I'm just going to leave those there. That way it's just kind of, I don't know, if I shift them over to a different day, I don't know. I like having everything on the Friday. It looks better to me. Okay. So as you're working these problems, the next time that we're together, even though we're going to be moving on to module 5, the first part of the class, I'm going to ask, what questions do you have on the homework from application or from module 4? Okay. What do you have for the homework? Now, notice here, module 4 does not have a connect, so don't worry about that. And then also notice that tomorrow night expires module 3 application problems and practice problems. So if you're, you know, kind of in that grace period time right now, you still get full credit by handing in by 11:59 tomorrow night for application problems 3. Okay. Jack's like packed up, ready to go. I'm out of here. I know we're going to be done when Kelly's done talking. All right. So that's all that I have for this evening. If anything comes up, I'll kind of hang around if anybody has any questions. But otherwise, good night tonight. We got through a lot.